Hello everyone, my name is Friederike and I want to talk to you today about NF-core Sarek, which is a pipeline for germline, tumor-only and somatic variant calling and annotation of short read paired end data. Sarek is part of NF-core, which is a community effort to collect best practice Nextflow pipelines. It consists of three big blocks, mainly the pre-processing based on GATK best practices, variant calling with various different tools for SNP indel, structure variant, microsatellite instability and copy number calling, and annotation. And then last but not least, a bunch of quality control tools are run throughout the pipeline and collected in a multi-QC report at the very end. The variant calling consists of three tracks. The blue one is for germline only, the red one for tumor only, and then the red and blue one for paired variant calling. As you can see, we have many different tools that are supported, and they can be run in any combination all together, and mix and match, and they are all run in parallel. As I mentioned, the pipeline is for short read data only, for paired end data, and it can be run with for any organism for which a reference genome exists. So we have a lot of reference data packaged with the pipeline for human, mouse, and a bunch of other organisms, but also for organisms that we don't directly support, the pipeline can be used. Sarek has been part of NF-core for quite some years, and recently we rewrote the entire pipeline to make use of DSL2. So this has been an involvement of the Nextflow language to enable code sharing between pipelines and a modular implementation. So this allows us to share tools between pipelines and have a community curated set of Nextflow wrappers around common bioinformatics tools. And throughout this rewrite, we also attempted to optimize the pipeline, which is what I want to show you for the rest of my short presentation here. So one of the things that we looked into was reducing storage space that the pipeline needs. So Nextflow pipelines, you need intermediate storage to enable things such as resuming the pipeline, which is really useful because if the pipeline fails for whichever reason on a sample, you can pick off where you left and you don't need to recompute already successful steps. However, this accumulates a lot of storage space over the lifetime of a pipeline run. And using CRAM files, we were able to reduce this storage space by about 2/3. It does come with a slight increase in memory. However, in practice, we didn't experience any problems with this as the memory usage is distributed over thousands of processes and is very short-lived, whereas the work storage accumulates over the whole pipeline run and thus can be a bottleneck if it's too much. Then the other thing that we looked into is scatter and gathering. So Nextflow itself will parallelize over all input samples accordingly. And then what we further looked into is dividing files of one sample into smaller files and processing those in parallel. So one of the things we added during the rewrite is splitting of the FASTQ files before mapping, and this allows us to use much smaller machines for mapping. It reduces the runtime overall. It does increase the intermediate storage space by about the input FASTQ size. However, the added runtime has been a big benefit to us. And then the other thing that has been part of Sarek for a long time and is also recommended by the GATK guidelines is to run base quality recalibration over intervals, so over genomic regions, and parallelize via that, and the same for variant calling. And in previous versions, we had a very high number of interval groups to be processed in parallel, 124, and what we saw is that this massively increases the storage space needs. However, it only gives us very marginal runtime increases. So instead, we have now severely reduced the parallelization across interval groups towards 21. And this leads to further storage space decreases by a factor of 5, as well as the decrease in runtime due to the mapping process. Then one of the aspects we are particularly interested in is how the cloud computation costs are developing for the pipeline such as Sarek, as genomic data is more frequently now processed on private or commercial clouds. due to the huge amounts of data that are available, especially for already publicly available data. And what we saw is that we could decrease the costs by about 2/3 between Sarek 2 and Sarek 3, and this should enable researchers to use the pipeline in the cloud more frequently. We also benchmarked against common truth datasets such as Genome in a Bottle or from the SEC2C consortium, with results as expected. If you have any questions, then contact us at NF Core or via the conference website, and I'm looking forward to connecting with you.